All right. Well, thanks for your patience. I'm going to start today presenting about, hang on, sorry, just a little bit longer. Sorry, guys. Okay. I wanted to make my title slide immutable, but that didn't work out very well. I had to change it every time, make a new one. But as you can see, I'm going to talk about immutability today. We've had a lot of presentations recently about functional programming, Scala, F#, Erlang, Akka, so on. So I wanted to talk about one of the core principles of functional programming and being immutability to help us get a better understanding of some of these things we've been seeing. So to start with, I'll just do a little bit of review. I think we're all familiar with the basics of immutability. It's an object whose state can't be changed after it's been created. Has anyone not ever heard of what immutability is? Just curious. I want to make sure I'm not going too fast. So here are some examples of immutable objects we've worked with in the past in .NET. Strings and datetimes and timespans I think everyone is probably familiar with, but some things I didn't realize, like tuples and anonymous types even, are immutable. So when you create anonymous types, when they're created by the compiler, they'll actually be immutable. You can't modify it once you've created that. That was something new I learned. As opposed to that, some mutable objects we've used, collections, of course, streams, database connections, the IOC container we work with, that kind of stuff. Usually the different objects we create are all mutable. Can anyone name some other immutable types we use from time to time?
You say other?
Yeah. Other immutable types? Think of any of the value types you use, like ints, longs, those are all immutable since they represent a single value. But instead of going over basics of immutability, I'm actually going to talk about immutable collections today. This was something that kind of confused me when I first heard about it, because when I thought of what an immutable collection was, I thought it's a collection that can't be changed, and that didn't really make sense to me, because why would you want to have a collection that you can't add or remove things from? But it actually, if you think about it from how you use other immutable types like strings or datetimes, it just means that as you work with it and you want to modify it, you get a new instance back every time. So the same way, if you concatenate a string or take the substring, it gives you back a new string. If you add to an immutable collection, it gives you back a new collection. And so that gives us some interesting advantages because you're not modifying the existing collection. It stays the same, and it's basically a snapshot at that point in time. And that makes it thread safe. And it makes it very easy to use in a concurrent environment where you have different things modifying it or reading from it at the same time. But that also means there are some performance trade-offs. So to start with, let's play around with making our own immutable collection. And we'll start with some tests. I'm going to call this the slow immutable list because we're going to do this in the simplest possible way. We're just going to create a collection that wraps a list, and every time we change it, we'll just copy it and return the new instance. So let's write a few tests for this. Let's say that as we add to the collection, we're not going to modify the original list. So let's say we have our first list, which is a new slow immutable list. And we'll say we're going to just test it with ints. And since it's immutable, when I modify this, we'll get back a new one. I don't have an add yet. I guess that'll have to be the first one we do for this to actually really be a collection. And let's just check that once we add to the list, it actually has something in it. And let's make sure that the original list is still empty. And since I don't even know if count works, let's just be crazy about this and check that too. All right, and while we're at it, let's go ahead and, oops, sorry. Let's go ahead and do remove at the same time. So we'll start with a list that has some items in it.
Everybody should take notes. He is using
Yes, I'm using it. And you can see I'm failing at it. Or I guess just to say resharper, it's killing me. Why is this not? Yeah, but when I tried to, it was resharper was kept auto-completing for me. Okay, so we're going to say we'll also allow the immutable list to be initialized from some other set of values. So let's start it off with like, here we go. So we've got just a small array of items. When we go remove something from there, let's remove the 1. Now this 2's count should be 3, right? So that means list 2 shouldn't contain the 1. And check the original list. Anyone tell me what comes after 3? 4. Sorry, I thought you could count faster than that. Okay, so we've got a couple tests there. This will be the interesting thing. We're going to test that this immutable list that we're going to create is actually thread safe. That it's better than just using a plain old list because we can actually have something enumerating through it while something else is modifying it. So let's create a little list here. Actually, let me just go yank this line up here. Yeah, out of Impro, I can copy lines. So the only reason I'm manually getting this enumerator instead of doing a for each is because I'm going to interrupt the iteration right here and modify the list. So we'll do our first move next, and that should be true, right? Because there's something in the list here. And then we're going to actually modify this. So we've got another 1 added to it now. And we'll just say that when we enumerate a second time, it doesn't throw any error. Normally you get that collection was modified error that you can see. I can't remember the name of the exception. Okay, so we've got some tests, and they fail because they don't even compile yet. Let's go implement these. So we'll start with our inner list that we're going to wrap. That's easier to do than creating our own data structure. And I guess I'll just say it's I list of T. And we need the constructor to just give us an empty list, right? We also need that constructor that allowed us to pass in an existing collection. So let's say this just takes some iList. And that'll be our inner list. And then let's go add our count. Which is really easy because we're just wrapping this one. And we'll have our add. And to add, we're going to have to return a new one. Okay. I'm not sure what I just did there. So remember, since we're immutable, we're going to clone this list every time we modify it. And then we'll modify the copy instead. And we can return that. Or I should say, we're going to return this guy. So remove is pretty much the same thing. We have to copy it first so that we remain immutable. We'll remove from the copy. And then we'll return a new list with that in it.
So just to be clear, like let's say your key was some kind of object.
Yep.
When you do your toList and create that copy of it, the pointers for the objects within that list, it's not like deep
It's a shallow copy.
Yes,
Yes, it's not a deep copy. If you wanted to do a deep copy, you would have to manually whip through that, make sure whatever object it is that's in there is something you can clone, and clone each and every object.
Yeah. I figured. I just wanted to be really clear about that.
Yeah, with an immutable collection, you get immutability at the collection level, and it guarantees that the collection itself will be thread safe. And if you really, really want everything to be completely thread safe, you would just want to make sure that whatever you're storing in the collection is also immutable. So like if this was an immutable list of strings, then I can't change anything about that. So one last piece before this test will compile, we need to make it enumerable. So let me go do that. Because it's a collection, right? It should be enumerable. And we'll just say that we're going to use our inner list and enumerate over that guy. Because we're copying this here, we've guaranteed that our inner list is never going to actually be modified. We'll just return that enumerator. So all these tests should pass now, I think. All right, so that shows us a very, very simple immutable list. Can anyone tell me what problems it has?
Slow?
It's slow, yes. Thank you. It's even in the name. So why is it slow?
Create an intermediary data structure at each step.
Yes, and it's not an intermediary data structure. It's actually used in the new instance of the list. But yes, at every single step, you are copying the whole list. So what would happen if I wanted to add 1,000 elements to this list? That means we're going to be copying it 1,000 times, and that creates a lot of garbage in memory of data we're never actually going to use because it's never even returned from this method. So that's just extra garbage. So that brings us to another option we can do, and this is something you'll be more familiar with if you've used immutable collections in a functional program, in a functional language. And I'm just calling it a functional list. So a functional list, if you're not familiar with it, has a head and a tail. It's similar to a linked list. The head is the first element in the list. The tail is just yet another functional list representing the rest of the list. So we'll do the same test here to create that functional list, and then I'll show an implementation of what that looks like. To start with, we'll just say that we can add to it. So let's do our List again, this one's going to be a functional list of type. Let's just stick with int. And our second one is that we're adding to it again. And then list 2 shouldn't be empty, right? And just to demonstrate what the count would look like on a functional list, we're going to test that too. And let's go do the remove at the same time. And to start with, I'll just add a couple elements to this list to give us something to start with. List 2 equals list remove 2. So that means the initial list shouldn't have been modified. Just for a sanity check, I'll do something like that.
I think that should be true.
Yeah, should be too. Thanks. Q, true. So our modified list should only have 1 in it. And contains 2 should be false. Wow. Auto completion for the lose. Okay. So this one also doesn't compile. Let's go implement our functional list here. So we'll start with creating our little empty guy that indicates the initial state for the functional list. And because you can only really have one empty functional list, we'll just make a singleton one. And that means we'll make a private constructor for that. And then we'll also create another private constructor, that allows us to create new copies of the list as we modify it. So we're going to take the head and we're going to take the tail from the previous list. Sorry. Let me go make these properties before I fill in that constructor. Or I should say I'll just make them fields. So these are all read-only fields, which means this data type is immutable. We could try going and changing that with reflection or something, but we're going to use it normally. It's definitely immutable. And that means, oops, up here I need to say that isEmpty is true. So and those of you that have done the Scala functional programming course will find this really familiar. I'm just doing it in C# instead. So in order to add, we need to create a new list. And this one's even easier to do than the last one. You don't have to copy anything. You can just pass in the added item as the new head and ourselves as the tail.
So it prepends it to the list?
Yeah, you could say it's prepended. It just depends on what direction you're thinking about it from. We'll get into that when I'm done with this. I'm going to talk about some of the performance characteristics. So to remove, we need to check some stuff. If we're empty, there's nothing to remove, so we'll just return ourselves because we're the empty list. If our head equals the item we want to remove, then we can return our tail. And then otherwise, we need to remove it from the tail. So what I'm showing here is another concept from function programming using recursion, and the functional list lends itself very well to using recursion. Since we have a head, which is just one item, and a tail, which is all the other items, we can do things piece by piece. When we need to remove an item, all we need to do is check our head. If the item doesn't match that, we'll just tell the tail to go remove it from there, and then it kind of recursively comes in here. So I had a little comment in here for my example. You're right. I missed one last thing on here. I was staring right at it on my notes, but missed it. So yes, now we have the head, and we're removing the item from the tail. So that's just going to recurse through the tail until it gets down to either the empty list and the item wasn't even in the list in the first place, or it's going to go remove it from that piece and include everything else. Can anyone tell me why this isn't tail recursive?
Tail recursion implies that the single expression is just a call to yourself.
Yeah.
Your expression has an additional add-on.
Yep, that's right. So with tail recursion, I'll let you guys go look it up if you want to know more, but it basically means that the very last operation of your function is a recursive call. But it has to be the very last operation. And so this recursion over the tail then calls add. So we're not actually tail recursive here. So let's see, what are we missing from our test? We still need to do a count and a contains.
The reason tail recursive matters is because the compiler can be smart with your stack.
Yeah, as you're using recursion, that's adding more and more frames to the stack until you get a stack overflow. And with a list or some other collection holding a lot of items, you could very easily overflow unless your operation is tail recursive, in which case the stack at that point doesn't grow and grow and grow. Let me scroll down some more so you can see that. So we could be caching the count and returning that. I just wanted to show a more functional approach to doing the count, like using recursion yet again. So this is also not tail recursive since we're doing the add after we call count on the tail. But is this stuff starting to look familiar between these few methods? We have a couple cases. This would be where pattern matching comes in handy if you're using a functional language. Because we're doing it yet again in this method. We're going to check if we're empty, which would mean we're going to return false. Then we can check the head, And I have to use equals rather than the equals operator because it's a generic parameter. The compiler won't let me just use double equals. And so yet again, we can just recursively call up tel and ask our tel whether or not it contains the item. So this is a very common pattern here. We're checking a couple different cases. We're either an empty list or we're a list of an item and some other items. And we can just pass down to the tel. And now that that's all implemented, let's check these tests here. Yeah, so those pass. Yeah. So let's take a look at some of the differences between these two lists. Can anyone tell me what the big O would be to add to this slow immutable list? We kind of talked about how you have to clone the whole list, so the big O is going to be n since we're going to iterate over every item in the existing list and then add the new one. Removes the same thing. It's a big O of n because we have to copy the list. The count would just be a big O of 1 because it's just one single operation of returning the count. What would the big O be if I wanted to create an indexer and index into this list?
You'd have constant time lookups. Just
Yeah.
Already got here.
That's right. Since we're wrapping this list, we could just use the indexer on this list and we'd have constant lookup. So how about for our functional list here? If I wanted to look up at some index in this functional list, what would the big O be? Yeah, potentially n. We'd have to loop through the list until we found the item until we hit that index. What's the big O for add? Yep, that's constant. It's just one operation of creating the new list and setting the head. This is also much more memory efficient because we're reusing the tail and sharing it around rather than copying the elements. What would the big O be for a remove? Yep, that's n as well. We have to loop through it potentially to the very end.
In this case, maybe n plus something. You've got additional add operations.
Yeah, but that's the coefficient that goes in front of the n. We just chop it off.
Okay.
But yeah, it could be like 2n or potentially a couple operations, but it simplifies down to a big O of n. How about for the count? Yeah, that's also in. Like I said, if we wanted to be smart about it, we could just cache the count, and as we create a new list each time, we just update that number, so we won't have to iterate through it every time just to get the count. So that shows one way that's used in functional languages to create immutable lists by using the head and the tail, and you can work with them recursively. Another way that lists get created are by using trees, binary trees that are either sorted based on the elements, or they're kept balanced based on what was inserted into them. So in this example, we have a binary tree of integers, and it's just sorted from left to right based on the value of the integer. So in a binary tree for immutable lists, we get some advantages because we don't have to copy or clone the entire list just to add to it. Instead, we only need to modify the nodes that actually change. So let's do a little exercise here with this immutable tree and go through what we would need to do if we're going to add the value of 11 into this collection. Does anyone want to tell me where we'd start with that to add 11?
For the root node.
Yeah. Okay, so where's my mouse? So 11 goes to the right of an 8, left of 13, right of 10. And then we need to modify it. So if we're immutable, we can't actually modify those nodes. Instead, we create new ones. So we create a new 10 node and add the 11 to it. Then, because we've modified the 10 and it's a new node, we can't modify the 13 to point to that. Instead, we create a new one. then we create a new root node for the 8 to point to the new 13. And this is what's known as a spine rewrite, because we're modifying just one path through the tree, and in a potentially large tree of many, many nodes and leaves, we're only updating just a small piece of it. So it's more efficient than having to copy and modify the entire collection. Instead of walking you through creating a binary tree example, instead I'm going to show an existing library that's up on NuGet that uses these collections as binary trees. And that's the Immutable Collections library from Microsoft. The NuGet package name is microsoft.bcl.immutable. It's a bad name, but the actual types are in the system.collections.immutable namespace. And they include these 7 different collections, and they all are implemented by using an AVL tree underneath. An AVL tree is a type of binary tree that is auto-rebalanced as it's modified, similar to the sorted tree, but instead it's just balanced to help with the lookup as things are changed over time. I'm explaining that badly. Before I get into that example, though, I'm going to talk about performance of the immutable collections. Because I've mentioned before, there are some trade-offs. Sometimes things might be faster, or sometimes things might be slower. So this is an example of the add operation on the various immutable collections that are included in that package. Just to add to the collection, the typical immutable collections that come in .NET, usually the add is a constant time operation. Although in the worst case, it's no event, because if you hit the capacity of the underlying array or whatever collection is stores the actual data, it ends up having to grow that array and copy all the elements into the new one. For example, especially with lists, you're probably most familiar with the items in a list are stored in an array under the covers. That array has a fixed size because arrays can't grow. So if the list gets bigger than that array, it then has to double the size of the array and copy all of those items from the first into the second array. So normally it'd be a big O of 1, but in the worst case, it'd be a big O of n. And that's where you run into thread safety issues as well, as if things are trying to modify the array as it's being grown. That's why it's not a thread safe collection. Whereas with the immutable collections, it's usually a big O of log n, and the log n is just because we're doing that spine rewrite and only modifying a part of the collection, where everything else remains the same and can be shared. So we get some memory efficiency there too, as we can share any items that weren't modified. And that's about it for the slides. Let's go into some code and play around with the immutable list. I have a test here. Sorry, I just want to make sure this really did pass. Okay. I've already written this test. I didn't want to take the time to write it while everyone was watching, but we're going to implement an event aggregator, and we're going to use an immutable list to store all the event listeners. Because this is a good example of where we would want to use an immutable list, as we need to loop over all those listeners whenever we want to publish an event to them. But we could also have things that are trying to add or remove subscribers at the same time. So to start with, let me show you what happens if I try to run this test right now. I'm going to use this mutable event aggregator down here. It's just storing a list of listeners in a regular old list. So to add, we just add, remove, remove. When we publish an event, we want to find the listeners that listen for that event and just call the handler on each of them. Then in my test, what I have going on here is a task running on another thread that is going to be adding new listeners to the event aggregator as time goes on. And meanwhile, we have this that's trying to publish events. When I run this test, this is really hard to show here. We have this error that we've all probably seen before. If you're trying to enumerate over a collection that's been modified, it blows up. And that's happening because we have down here added a new listener as we were in the middle of looking through the listeners to publish events to it. So let's use our event aggregator and implement something that is going to be thread safe. So this is going to kind of demonstrate how easy it is to use these immutable collections, and it doesn't make the code much uglier than it already was. In this case, the only difference is that we are setting the field to the new list. The same thing with remove. So that's almost exactly the same as the other one. And the publish is the same as the other one. We're going to find the listeners that handle this type of event. And we're just going to I'll publish on each one. Or, sorry, handle. So that's the same thing as our mutable event aggregator. The only difference now is that we're setting the new value. But that's still pretty easy to read. You don't have to worry about locking the object or using a reader-writer lock or that kind of thing to manage concurrency access to this collection. All we do is just add to it and save the new one. And let me rerun that test. Now it passes. So we were modifying that. Every time we called publish, we're using a current snapshot of the immutable list, and we're publishing the event to whatever listeners we had at the time. If new listeners are added or if listeners get removed, that'll apply to any new messages that are published. But for this case, we just have that little snapshot. And then the object reference will just change as we modify the collection. Does anyone have any questions about that? Yeah, okay. Can anyone spot the race condition in this code? Go Zach.
If you remove yourself and then you get sent a message, it's possible that you could
Yes, that's possible.
yourself and then you get a message and it goes up on you.
So you're saying if you're a listener and you are removed and right at the same time you get an event past you, I guess you could call that a race condition.
Not sort of, I don't know if that, but it's could that
I
be
just
a
call
problem?
that a nature of using the immutable collection.
Yeah, I mean that could happen. I mean, even if you are using, like, say I was using a concurrent bag or something instead of an immutable list, I could still get some event after I had called remove just by the order of execution of the program. If I called the remove method, then it hadn't quite taken the lock and modified the collection. Some other event could come in and call me.
Is the race condition if you add and remove maybe at the same time with two different threads?
Yep, you got it. So we are adding, that gives us a new collection, and then we're then saving that collection to this field, this object reference. And as Mike said, if we are doing two modifications at the same time, we could have the same old instance get modified and return a new one to us, and then we've lost one of those changes. Either if we add multiples at the same time, or if we're removing and adding, or that kind of thing. So if we have more than one thread writing at the same time, we have to lock down access to the update of this. And that's where immutable collections would have you use the interlocked library to update that. I actually have an example here. I didn't want to do this live, so I wrote this earlier, of using a cache with an immutable dictionary. So this is a cache very similar to the cache we use in FubuCore all the time. So you can provide an on-missing func that'll automatically get a value and fill the cache if you request something that's missing. So it's a dictionary on steroids, I guess you could call it. But what happens is that as we are modifying, there's these helper methods in the immutable collections library that allows us to make sure that the actual reference we have to the collection is updated in an atomic fashion. So if something is adding to it right as we're trying to add it to it, it'll try a second time and it'll continue until it actually has an updated reference with all the changes together. So that's how you get something similar to using a concurrent dictionary where you have the get or add or update changes in there, or trying to remove from it. So this is really straightforward, not too many lines of code for this little cache here, and we're also thread safe. So it all depends on your scenario. Maybe you want to use the concurrent collections from system.collections.concurrent rather than an immutable collection, or maybe you just want to use a regular old mutable collection. It's going to depend on your use case, what kind of performance you need to worry about, or if you want to just do it with something that's most readable code and most maintainable, and then you can measure later and see if you really need to optimize for performance in that case or not. The reason I thought an event aggregator was a good example of an immutable list is that you're reading from that a lot more than you're writing to it. Usually you add listeners occasionally, maybe on app startup or that kind of thing, and then most of the time you're just reading that collection and whipping through it or that kind of thing. Same thing with a cache. Caches are read from much more often than they're written to, usually. So an immutable collection would be helpful there. Any other questions? Who wants to go use immutable collections now?
So how much performance do you trade off? Because I seem to remember I had a blog post about that a while back.
Yeah, so Allende had a blog post talking about how slow immutable collections were, and he had a very specific use case that they weren't necessarily designed for. When he was comparing a dictionary, a concurrent dictionary, and an immutable dictionary, I think, and saying that the immutable dictionary was way, way slower. You're really just going to have to see how it works for you. I was watching on Channel 9 a video where they dived down into the implementation of the immutable collections NuGet library and how they were implemented with the AVL tree and stuff. And they were talking about how if you're in a very highly concurrent situation where you're doing writes from a lot of different threads and stuff, the concurrent collections are highly optimized for that scenario. So it might be better just to use those. But if you're in normal cases and you want the thread safety, so you don't have to worry about whipping through something, or if you find your code has a lot of to-list calls before you go use it because you want to get a copy, the immutable collections are really useful there because then you don't have to take that cost of copying the collection and that kind of stuff. And it'll be a bit slower to modify those collections than it will be to use their mutable counterparts, but you may not really notice that cost or be fine with paying it. And also one thing to mention, this is C#, and there's a great new Git package for it now, but Bob also just told me about the immutable JS library, which is a JavaScript package you can use from Node, and I believe just from plain old JavaScript too.
Yeah,
but
that seems to be like less
pure JavaScript.
type thing. Like Facebook's just put it out. Not
Yeah.
using it internally yet, but they're working on it.
And I thought I had it up here. I don't. Here's the NuGet for that. But there is on GitHub under Facebook's account, there is an immutable JS library, which is really new. But it has a lot of immutable collections for JavaScript.
I guess that's for code, right?
Yeah. Or for JavaScript in the browser, yeah. Oh yeah, I guess that's true. You have the background workers now, though. Sort of, yeah. Any other questions? Great, that's it for me.